We are moving to the next presentation, and the next talk will be given by Denis Herasymuk. I see he's preparing on site. Oh, perfect.
Can you hear me?
Yes. So we can hear you. We don't see the slides yet.
Yeah, I'm sharing 1 second.
Oh, perfect. We see the slides. Excellent. So Denis is a senior data engineer at EPAM Systems at a company, and also a visiting research fellow at the NYU Tandon School of Engineering. And he's going to talk about his work on model auditing and responsible model selection, which, as we all know, it's a very important problem and timely in these days. So Denis, it's great to have you give a talk. The stage is yours. Thank you very much for joining us today.
Okay. Yeah, thanks. So hello, everyone. As I said, my name is Denis, and I'm research fellow at the Center for Responsible AI at NYU, and also a participant at the Responsible AI for Ukraine program. Actually, I also had some slides about this program. You can check out this link to see our website. And today I'm very glad to present our paper accepted to SIGMOD 2024, which is called Responsible Model Selection with Virne Review, which is joint work with Fala Rivhan and Julia Stoyanovich from New York University. And let's begin with the motivation of our work. So motivation is straightforward. Accuracy is not the only important dimension of model performance. And the reason behind that is that model predictive error can be decomposed into bias, variance, and noise terms. While accuracy metrics can capture the bias term, they fail to capture variance and noise terms. But variance and noise terms are quite crucial thing because they are related to such dimensions of model performance as stability and uncertainty. So model stability measures whether small perturbations in the input cause proportionally small changes in the output, whereas model uncertainty captures the confidence of a model in its predictions. And model's instability and model uncertainty stems from two main sources. The first one is the inherent randomness or variability in the data. And the second one is a lack of information arising from limitations in understanding the system or process being modeled. To better explain that, I added this visualization. So here you can see in red line real function, and in blue dots we can see our training data. So when we have a small variance of our data and these data points are quite close to our real function, so we have actually low aleatoric uncertainty or data uncertainty. But in areas where we have a bigger variance of our data points, so we have high aleatoric uncertainty. And in areas where we don't have enough data, we have high epistemic uncertainty or model uncertainty. So also in literature, it was observed that ML models can exhibit disparities across groups in terms of selection rates or error distribution. And these disparities actually can lead to unfairness in real world and even to unlawful discrimination against historically disadvantaged groups. But actually, overall accuracy metrics cannot capture a model's potential discrimination against demographic groups. And therefore, it brings us to the importance of measuring error disparity metrics. So it's our standard accuracy metrics, but measured for specific subgroups. And even popular fairness metrics, which were provided before in literature, don't actually capture whether the model is comparably stable and certain for different demographic groups. And this leads to such important metrics as stability and uncertainty disparity metrics. Based on this motivation, we define the next problem for our work. So since measuring only accuracy is not enough for building responsible ML systems, each ML model has at least 4 dimensions of performance, like accuracy, stability, uncertainty, and fairness. So this brings us to the following challenge. So considering the multitude of model types, performance dimensions, and trade-offs, we face the challenge of responsible model selection. So challenge when we need to select the most appropriate model for the context of use. And actually, these dimensions can have trade-offs with one another. Therefore, we need to understand what among these trade-offs we need to choose for our context of use. And in this work, we present the following contributions. So the first contribution is the following: that's our software framework, which is called VIRNI. It measures all these normally important dimensions of model performance, which is fairness, stability, and uncertainty, both overall and broken down by groups. The second contribution is that VIRNI enables data scientists to analyze performance using multiple sensitive attributes, including non-binary and their intersections. The third one is that VIRNI offers diverse metric computation interfaces for in-depth profiling of model performance. And the last one is that VIRNI implements streamlined flow design tailored for responsible model selection. And next, I will explain two of these four contributions, which solve the following two subproblems. The first one is how to measure these metrics, and the second one is how to streamline responsible model selection. So how to measure these important dimensions of model performance? One of the dimensions which we measure in VIRNI is model fairness. In general, the term group fairness means the absence of any prejudice or favoritism toward a group based on their intrinsic or acquired traits in the context of decision making. And there is such thing that there is no one definition of fairness. Multiple definitions of fairness exist and actually are necessary, because what is considered fair depends on the domain. So are you providing a loan, or is it related to university admission? So it's actually quite different domains, and fairness criteria for them can be different. So they are context dependent. So it also depends on the legal and social context. And each fairness criteria is expressed via its own fairness metric. So here, for example, we have three example metrics: equalized odds FPR, equalized odds FNR, and disparate impact. And as you can see, in general, it's just differences or ratios of our previously accuracy metrics, but for specific groups. For example, here we compute this metric for disadvantaged group, historically disadvantaged group, which can be like non-white races, and for historically privileged groups, which can be white races, for example. And in addition to fairness, VIRNI is able to measure model arbitrariness. And in our approach, we are using bootstrap methods to quantify model stability and uncertainty, since basically we were working with tabular datasets, and the bootstrap method is one of the most popular ways to measure this in the case of tabular datasets. So how it works, it's quite simple. So we firstly obtain M bootstrap samples by randomly sampling the training set dtrain with replacement. Next, we fit each classifier on the appropriate bootstrap sample and apply M-fitted classifiers on the same feature test set dtest to obtain M prediction sets. And in this way, as previously we had just one prediction for one row, using Bootstrap we will have M predictions for one row. And in such a way we can get this variance, predictive variance, which we actually will use to compute various types of metrics. So it's stated that using So in such a way, we obtain the predictive variance, which approximates the model stability and uncertainty of a single model being used to make predictions. And based on this variance, we can compute the following metrics. So the first one is called label stability, which is just the difference of the number of models that classify a sample as class 1 and the number of models that classify a sample as class 0. Additionally, we can compute other uncertainty metrics, which one is epistemic uncertainty or model uncertainty, and this is just variance of our model predictions for a specific sample. And also we can compute aleatoric uncertainty, and in this case it measures the inherent uncertainty in the data, measuring Shannon's entropy. And we incorporate and build the following software framework to measure all these metrics. So in general, the framework splits the whole pipeline on 3 stages. The first one is subgroup metric computation. The second one is disparity metric composition. And the last one is metric visualization. And the process starts when user defines 3 types of inputs: base flow dataset, models config, and config YAML. And these 3 inputs go to our metric computation interface. There is a rich set of various types of metric computation interfaces depending on the context of use. But for example, here, next we apply subgroup variance analyzer and subgroup error analyzer to compute actually all these overall metrics and metrics for different disadvantaged and privileged groups. And as output, we get our pandas data frame, which goes to metric composer. The idea behind metric composer is that it computes disparity metrics based on previously computed metrics for disadvantaged and privileged groups, because as I previously showed, that it just differences or ratios of our accuracy metrics, and there is no need to recompute the whole pipeline if you need to get just one new disparity metric. And also in such a way, we can save storage and computation time for that. And next, we pass our 2 pandas data frames to metric visualizers. There are several types of visualizers. There's one static, another interactive visualizer, and we actually use them to build our Virni view tool. And to better show what results can we get using Virni, I added here slightly plots from another paper. So in general, what is shown on this plot is we conducted the following experiment. We took different train set sizes and use the same model and use the same test set. And we wanted to look what will be the trend of label stability when we vary these train set sizes. So, and idea behind this plot is that when you increase train set size, your model stability actually increases. And it's quite a logical observation, which there is like proofs in theory, but we could not find any papers that showcase that in empirical studies. And using Virni, we were able to show that. Also, we can see for trends for epistemic uncertainty. So when we increase train set sizes, epistemic uncertainty or model uncertainty actually decreases. What about aleatoric uncertainty? I can remind that it's data uncertainty. So as you can see, it improves only slightly. The smaller, the better. And next, after specific threshold, it does not change. And the reason is that aleatoric uncertainty cannot be improved adding more data, which is quite well-known fact, but here it's empirically proved using our framework. So the second problem which we solve in this paper is how to streamline responsible model selection. And I need to highlight here is that Virni was not built to do responsible model selection on behalf of the user. And so in general, it just provides a tool how to speed up this process. And the user, now in the context of use, can apply this tool to make this process a little bit faster. So for that, we built an interactive tool to streamline responsible model selection. It actually generates nutritional labels for our ML models. And it consists of 6 visual components, each corresponding to a step in the responsible model selection pipeline. So the first step of this process is to analyze demographic composition of the dataset, because it can provide some insights why we see such patterns of model performance. So firstly, we analyze data broken down by different groups. Next, we try to reduce the number of models to compare based on overall and disparity metric constraints. So here a user can define what metrics are the most important for us and what ranges of constraints we want to have. And based on that, we are able to find this reduced number of models that satisfy this constraint. Next, when we reduced it, we can now compare them more deeply using such heat maps for overall and disparity metric comparison. So here, for example, we can compare overall metrics of this like 4 models, and with colors we show what model is the best one. These colors are adapted to what is better for the metric. If the higher the better, so or if it's the higher the better, or it's the lower the better. So these colors can take it into account. And the fifth step is to generate actual nutritional labels for the selected model. So here we select one model and can break down its performance by different dimensions and protected groups. And finally, we generate summarized performance of a selected model across different dimensions and protected groups. We can set specific constraints, and if model cannot be in that range, which is enough for our context of use, it's marked in red. And based on our previous contributions, we see the following venues for future work. So first venue comes from the point that actually this bootstrap method is quite computation heavy process, and therefore we want to speed up measurement of model stability and uncertainty. And we have one ongoing project in this direction, which is called Virni Flow. The second one is that actually in benchmarks, which we have in fairness literature, there are no benchmarks that also try to measure not only accuracy and fairness, but also look at stability or model arbitrariness. Therefore, we create our own benchmarks to assess the impact of various ML lifecycle stages on model stability and uncertainty. And also, we have one ongoing project in this direction, which is called Shades of Null. And the last one, it's quite tricky problem because we want to integrate multiple dimensions of model performance, like fairness and stability, into hyperparameter optimization step. And it's quite not easy thing if you want to do something smart, but we still think that it's important for responsible model development. And that's quite all. Thank you so much for your attention, and I'm happy to take any questions.
Thank you very much for the very interesting talk. The work is very exciting. I will maybe again start if there are any questions in the audience. I don't quite see the audience, but maybe Rostislav, you can moderate the questions discussion.
Any questions, please?
So my question would be, you use Bootstrap to evaluate the performance of the models. Is there a specific reason to do that? Or, for example, one could also use cross-validation or repeated cross-validation. Would I have a small follow-up question then on that?
Yeah, so idea here is that before applying Virni, you actually why we use Bootstrap approach? Because Bootstrap approach is one of the most used approach to quantify model stability and uncertainty in context of tabular datasets, which are the most popular for fairness literature. And therefore we apply Bootstrap here. And the way how you can work with Virni is that you firstly tune your hyperparameters, for example, for accuracy metric. And after that, I can show on this slide. So it's like trained model with already we find the best hyperparameters for example, for F1. Next, in Bootstrap method, we already set the same hyperparameters for different estimators in our Bootstrap. And using Bootstrap approach, we actually can compute model stability and uncertainty because it provides us this variance, which we can use to compute such types of metrics which you provide here. So the answer will be that we use, but there are other techniques to compute uncertainty, and the thing is that they are more tied to deep learning, but in fairness literature, we have more tabular data sets, therefore we started with the Bootstrap approach, but of course we want to try other approaches and speed up our Bootstrap approach.
So did you, so you did perform the hyperparameter optimization before the Bootstrap? So,
yeah.
Okay, but isn't it possible that you get a little bit of an over-optimistic performance estimate because when you perform the hyperparameter optimization on the whole data set, then perform the Bootstrap samples and then use the optimized parameters on these Bootstrap samples, it could be that the performance is slightly overestimated. So
I understand what you're talking, and therefore model arbitrariness should took into account during hyperparameter optimization. Therefore, we define it. It's as interesting future work. But yeah, it's quite clear.
Yeah. So one problem with Bootstrap is also that there are the same observations occur several times in the Bootstrap sample. So oftentimes one recommends to perform subsampling instead of bootstrap, choosing bootstrap samples, because this does not happen then. But yeah.
But we're actually doing subsampling here. So actually, this bootstrap samples took this like 80%. Or each time we take a random 80% from our original trained data set.
Just the last comment, but in Bootstrap example, the same observations. So you draw in the observations, and in these Bootstrap examples, the same observation can occur several times. That was I meant.
Yeah. You can actually vary the percentage of how many you want to take into account for each bootstrap. It's like parameter invariant, but yeah, it's quite cool.
Key things.
Thank you. Any further questions from the audience? I may have a very small question. You started with fairness, and that means that the result of the model should be independent of the these sensitive traits. Yes. But on the other hand, you should ensure that your sample is representative. And typically, one just takes marginal distributions over several traits, but that's probably not what one has to look. Did you think, or did you ensure that the joint distribution of these sensitive traits are preserved in?
Yeah, so I understood what you're talking. So in general, Virni is just model profiler. We are not doing any type of optimization or tunings there. And so we just compute metrics based on that model that user provide to us. And as you said, in fairness domain, we cannot use sensitive attributes for training. You try to avoid them. In general, it's like you try to avoid sex and race columns in your dataset during training. But the thing is that it's not always help because we can have some feature covariance between feature correlation between features, and some other features can show that this for example, row is more likely that this row is related to male or female. And the thing is that in fairness, there are three types of fairness enhancing techniques which we can apply. It's pre-processing, in-processing, and post-processing techniques. And pre-processing techniques is when we try to change our data. Specifically, for example, it's like disparate impact remover. When we actually change our input data so that it satisfies a disparate impact metric, and after that we pass this data to our model. Another type of fairness intervention is when we have in-processing intervention. So it's actually when we change our loss function, so that we try to incorporate fairness criteria into our model's loss. And the last one is post-processing. Is when you, for example, your model tries to find like top 10 people for which we want to provide tutoring. And in this case, when model predicts 10 different, makes these 10 different predictions, we apply post-processing intervention, and it tries to so that, for example, in context of fairness for like sex, it tries to make that we try to select 5 males and 5 females. So it actually changes what predictions model did. So it's 3 types of interventions which you can
Thank you. Thank you.
Thank you very much.
I guess there is no further questions from the audience here. So
I think we are almost going to. I will ask maybe one more. So the software is available. Is it in a web server, or how is it available? Can you say a bit more about this?
Yeah. First of all, it's pip installable. Second, there is documentation. Third, our NYU lab is using this software to compute these metrics, because I try to make it very, very flexible. It supports 4 Python versions. It has integrations with the most popular software frameworks in fairness, like IF360. Also, you can profile PyTorch tabular models, which are actually neural networks, which could be applied for tabular data sets. So it's available, pip installable, and yeah, please use it. There are links actually in our paper. So yeah.
And maybe can you say what type of classifiers can you handle, just so that people understand, if it's applicable to their problem?
Yeah, currently we work with like only binary classification because it's the most popular in fairness, but we can extend it obviously to multiple class classification. And what types of classifiers? It's scikit-learn models, it's LGBM, it's, as I also said, it could be some models from PyTorch tabular, which is the most popular framework for neural networks on tabular models. So this actually quite good range of models which you can have.
So there is no, actually in the model, there is no assumption on the classifier form itself, right? It can be linear or non-linear, any type, because you just need to be able to train it on different subsets of data.
Yeah. And the idea of ERNI is to be very flexible to compute uncertainty and stability for anything that can be fitted and can return labels and probabilities. I was able to profile fairness in processors when actually loss function was changed. I was able to profile even such joint cleaning and training methods, when during training we also perform cleaning, which are actually quite hard models to profile, but Virni was able to do that. So yeah, we try to be very, very flexible in that sense.
Thank you very much for the very nice presentation. Thank you.
Thank you.
Thank you.